In the 18th century, one of the greatest scientific questions concerned the exact shape of the Earth and how to determine its shape. Isaac Newton had in the 17th century proposed a theory which predicted that the Earth was a rotating ellipsoid flattened at its poles. A disagreement arose in European scientific circles on whether the Earth was prolate or oblate. To resolve this question, it was suggested that the length of 1 degree of a meridian arc be measured near the equator and as far north as possible. To resolve the disagreement, King Louis XV of France funded 2 expeditions, one of which was sent to the equator in Peru, and the other to the far north of Scandinavia, to the Tornio River Valley. The expedition to the Tornio River Valley was led by Count Pierre-Louis Moreau de Maupertuis, carried out between 1736 and 1737. These degree measurements in Lapland are among the very first triangulation surveys conducted in Finland. The purpose of triangulation was to determine the length of the meridian arc on the top of the Earth, after which the latitudinal differences between the start and end points could be observed using astronomical measurements. The corners of the triangles were located on the hills surrounding the Tornio River Valley using quadrants developed by Langlois in France. The baseline was measured by laying a row of 30-foot poles created from spruce logs onto the ice of the Tornio River. The measurements produced the expected conclusion: the Earth is a rotating ellipsoid flattened at the poles, exactly as proposed by Newton. In the 19th century, another triangulation that had historical and scientific significance for Europe was conducted by Friedrich Georg Wilhelm Struve. Struve designed a triangle chain that extended all the way from the Black Sea to the Arctic Ocean. His objective was to determine more accurately the shape and size of the Earth. Measurement of the Struve arc was started in 1816 and was finally completed in 1855. Struve's chain arrived in Finland from Estonia, continuing to Jyväskylä along the shores of Lake Päijänne to the Tornio River Valley via Kajaani and Oulu. From Finland, the chain continued through the hills of Norway to Hammerfest on the shore of the Arctic Ocean. The northernmost point of the Struve chain in Finland, Stora-Oivi, features a cross engraved in a rock, marking the spot where the astronomic measurements were conducted. The actual triangulation points were principally marked with metal plates that were attached with melted lead to holes drilled into the rock. In 2005, the scientific historical significance of the Struve chain was recognized when it was added to the list of UNESCO World Heritage Sites. The Finnish Geodetic Institute was founded immediately after independence. Its main task was to measure the exact national coordinate system for creating accurate maps in Finland. To do this, the measurement of the first-order triangulation network in Finland was started in 1919 and completed in 1987. The National Land Survey of Finland also measured a large number of lower-order triangulations, and over the decades, thousands of people were involved in these surveys. The most visible part of the surveys were the observation towers, hundreds of which were built all across the country during this period. Great efforts were taken to ensure the accuracy of the survey. As a result, Finland today still boasts one of the most precise triangulation networks in the world. Triangulation is based on the geometric fact that if the angles and one side of a triangle are known, The length of the two other sides can be determined on the basis of these angles. However, in the case of a network of triangles, only the length of one side of one triangle is required. After this, the distances between all other points can be determined based on the angles alone. In the past, measuring long distances was necessary but rather challenging and time-consuming. Invar wires were used to measure these baselines, each of which was a few kilometers in length. Invar wire measurements were developed into an extremely precise method that took into consideration all possible sources of error. The length of a baseline, several kilometers in length, could be defined to an accuracy of a single millimeter. The most visible part of a triangulation involved measuring the angles of the triangles. The measurement of the angles was much quicker than measuring long distances. The angles were measured between neighboring towers erected for this purpose on large hills that could be located dozens of kilometers away. The process of measuring the angles always required an observer and one assistant. The measurements were taken by aiming measuring equipment at the lights beamed from neighboring towers. To attain the best possible accuracy, all angle observations were repeated several times. After the shape and the size of the triangulation network had been determined based on the lengths of the sides and angle observations, its real location and position in relation to the surface of the Earth remained to be determined. These locations were determined using astronomical measurements. For astronomical determination of the longitude, it was essential to measure the moment a star crossed the meridian of the observation point, while determining the latitude was based on studying the difference in the distance between various star pairs. By the early 20th century, this technique had become so accurate that the same method and equipment were used until the end of the 1980s.
Tässähän rakentuu perusviivan mittauslaitteisto.
Niin. Mutta näissä vanhoissa mittauslaitteissa on se kaikkein parasta minusta, että kaikki on näkyvissä. Ja nyt tänne toiseen päähän tulee sitten paino ja tuonne toiseen päähän tulee invarlanka.
Mittausporukka koostuu kaiken kaikkiaan 2, 4, 6, 7 ihmistä. 2 punttimiestä, 2 statiivimiestä, 2 havaitsijaa ja 1 kirjuri.
Mm-hmm. Täällä on yksinkertaisesti mitta tai lukemamerkki, mihinkä tuo nauhan lukema luetaan. Nopit kiinnistetään tuonne paalujen päin.
Näin. Täällä on tekstit ja muut karkein kielellä.
Mulla istuimiksi tämä sen.
Joo, laatikon kannellahan sitä on perinteisesti istuttu.
Näin. Kiinni on.
Sitten rupeat varovasti. Mä tätä annan tästä löysää. Hyvin menee. Pikkasen vasemmalle. Ota vähän löysemmin. Kummassakin päässä on 10 kilon painot. No, tää lanka on 24 metriä pitkä. Se on viritetty tähän paalujen ja mittausnuppi-indeksien väliin. Kummassakin päässä on 8 senttimetriä pitkä asteikko, millimetrin välein jaettu. Ja tämä lanka, kun se on viritetty tähän 10 kilon voimalla, niin se liikkuu tässä hyvin juohevasti noitten jousien ja pylpyrän yli. Ja havaitsija sitten arvioi millimetrijaotuksen perusteella. Ja samalla lailla samaan aikaan tekee sitten toinen havaitsija toisessa päässä. Lukemien erotuksesta niin saadaan tämä nimellispituus näiden paalujen välillä.
The angle observations did not provide any scale for the triangulation network. Therefore, invar wire measurements were needed to establish a baseline to determine the distance between two known triangulation points. By using the length of the baseline, the scale could be defined for the whole triangulation network. In practice, the lengths of the invar wires were first calibrated using the normal baseline located in Nummela. After calibration, inver wires were used to establish a baseline in the field, and then the length of the baseline was further extended using angle measurements. This then allowed the enlargement network to be established around the baseline. The longest side of the enlargement network is called the main side. It represents one actual side of the triangulation network, which could be as long as 30 kilometers in length. After setting the length for the main side, the work continued with angle measurements in the triangulation network until a new baseline was measured about 100 kilometers away. This ensured that the scale remained the same throughout the whole national triangulation network.
No niin. Onko valmista? Vähän alaspäin.
Valmis.
Hep.
493.
552.
Valmis.
Hep.
313.
371. Hep.
307.
365. Siinä oli se sarja. Sitten kirjuri joko hylkää tai hyväksyy ja sitten lähdetään eteenpäin seuraavalle paluvälille. Joo, no tässä pöydällä on nyt heliotrooppi-niminen laite, joka nimensä mukaisesti käyttää aurinkoa hyväkseen tässä kolmiomittauksessa. Tämän tarkoituksena on lähettää naapuripisteelle signaali. Havaitsija suuntaa tämän kojeen naapuripisteelle siten, että hän katsoo tästä pintapeilin keskellä olevasta reiästä peilin takaa naapuripisteelle. Ja nyt sitten tätä peiliä kääntämällä ohjataan auringon valo tuohon. Ja silloin aurinko heijastuu sitten tästä peilin kautta naapuripisteelle ja tuon reiän kautta naapuripisteelle. Ja kun maapallo pyörii akselinsa ympäri, eli siis auringon paikka muuttuu näennäisesti tuolla taivaalla, tätä peiliä sitten täytyy kiertää.
Sitten kun aurinko on hankalassa suunnassa, niin kuin tällä hetkellä tuolla takana, niin sitten käytetään tällaista apupeiliä, joka ruuvataan sopivaan paikkaan, vaikka tällä tavalla. Niin nyt tällä apupeilillä voidaan se auringonvalo tuolta takaa heijastaa tuohon peiliin, joka sitten heijastaa sen edelleen sinne meidän havaintopisteelle. Tämähän on tietysti todella kirkas, tämä heliotroopin valo, että se näkyy usean 10 kilometrin päähän todella kirkkaasti ja paljalla silmällä. Et tietysti huono puoli siinä on se, että pilvisellä säällä tätä laitetta ei voida käyttää. Ja tämä varmaan oli yksi syy siihen sitten, että viimeisinä vuosina näistä heliotroopeista tässä kolmiomittauksessa luovuttiin ja käytettiin sitten pelkästään akuilla toimivia lamppuja.
Täältä lampun takaa sitten tähdätään. Tässä on diopteritähtäin. Asetetaan reiän kautta näkyvä ristikko naapuripisteen kohdalle. Ja näin ollen tämä sitten auringosta riippumatta niin heijastaa tuon polttimon valon hyvinkin tehokkaasti sitten 40 jopa 50 kilometrin päähän. Tarkkuusteodoliitti, joka tässä nyt on tornipöydällä, on sveitsiläinen DK3, jota on käytetty kulmamittauksissa viimeisinä aikoina. Tätä ennen oli käytössä pitempi putkinen kaukoputki Hildebrandt. No niin, Vaaterinmäki. 211
211
30
30
020
020
040
040
032.
032. Hyvä.
Sitten Tammimäki. 273 04 804
804
800.
800. Hyvä.
Kylmäkangas, aivan oikein. Tuollahan se on. Valohan on ihan mainio. 336
336
46
46
550
550
540.
540. Hyvä.
Tämä oli nyt ensimmäinen puolisarja. Tämän jälkeen kaukoputki käännetään vaaka-akselin ympäri. Näin ja havaitaan niin sanotussa koneen kakkosasennossa samat suunnat takaisinpäin päinvastaisessa järjestyksessä. Ja näin saatu havaintoaineisto muodostaa yhden havaintosarjan.
Ja tässä oikeastaan kirjurin tehtävänä on sitten tarkistaa lennossa, että nämä lukemat, mitkä takaisinpäin mennessä tulee, niin ne poikkeaa sitten 200 goonia tai 180 astetta siitä, mitä oli toiseen suuntaan mennessä. Ja ainakin tällaiset karkeat virheet saadaan tällä eliminoitua sitten.
Lähes kaikilla ensimmäisen luokan kolmiopisteillä on havaittu 3 eri iltana sillä lailla, että kunakin iltana havaitaan 8 sarjaa. Ja näin ollen yhden pisteen havaintoaineisto koostuu sitten 24 sarjasta.
Now that the shape and size of the triangulation network have been determined using lengths of the sides and angle observations, we next need to determine the real location and position of the triangulation network in relation to the surface of the Earth. This was accomplished by conducting astronomical measurements using a meridian instrument. The meridian instrument consists of 3 main parts: a base, a frame, and a telescope. In addition, the instrument includes a number of levels to balance the device, as well as handles and a light to facilitate use of the instrument in the dark. After assembly, the instrument is balanced so that its vertical axle settles parallel to the local plumb line, and the device is directed roughly towards the north with a compass. After this, a more exact positioning is obtained by means of the polar star. Now the instrument is positioned parallel to the local celestial meridian level. The meridian plane is a circle that intersects the horizon at the observer's south and north points, while also intersecting the zenith. As its name suggests, the telescope of the meridian instrument is only moved along the meridian plane. Stellar observations are made based on astronomic observation lists, which have been prepared in advance. The exact determination of time is conducted with a chronometer that ticks away next to the meridian instrument. Astronomic observations make it possible to determine the deviation of the chronometer from the local sidereal time. The chronometric measurement is compared with the time signals received by radio, indicating the difference between the time shown by the chronometer and Greenwich time. Calculating the difference between the local and Greenwich sidereal times enables the degree of longitude to be determined for any particular observation site. The actual time at which a star passed over the meridian plane was recorded using a telescope and a chronometer. The ticking of the chronometer indicated to the observer the exact time, while he simultaneously followed the movement of the star in the telescope's visual field. As the star passed, the observer called out the time to the assistant.
52,7. Ja 7,5. Sitten mainitaan tuolta.
After this, the device was rotated in the opposite position, and the observations were repeated. In order to successfully determine the astronomical longitude, it was necessary to observe a set of at least 18 stars. In practice, it took about 2 hours to measure all 18 stars. After this, the local latitude was determined by measuring the height difference between various star pairs. Even a small set of observation points provides a good approximate estimate of the position and location of the triangulation network. In Finland, the astronomical positions were determined for all first-order triangulation points, which means that a total of 350 observation points were used. Exact information on the location, neighboring points, and visibility of all triangulation points and towers was documented in triangulation point registers. These registers also included other information, such as places of accommodation and instructions on how to get to the site.
The triangulation point lies near the Svartå station in the parish of Inkoo. The hill is quite large. It ascends steeply along the south side, but less so to the east and the north. According to a topographic map, the peak rises to 90 meters. The hill could be reached either from Inkoo or the Svartå station, following a road between the stations up to the crossroads where a small village road leads to Linkulla. By following the road, the men reached a group of small farmhouses at the foot of the hill where they had to find accommodation. For officers, Kramer's mansion, located along the main road a couple of kilometers from Svartå station, was an excellent place for accommodation.
In the early 20th century, no proper topographic maps existed for Finland. The first challenge in the planning of triangulation was to identify suitable sites for triangulation towers and to check their visibility from other points. Verifying the tower's visibility from neighboring towers, also known as recognition, was conducted by constructing a temporary recognition tower at the planning site. Alternative methods included treetops and ladders.
The Kärkelä Tower and the forest are clearly visible at the height of 10 meters. At the height of 27 meters, the tower of Valk Hill is visible. The Porkkala lighthouse is nearly completely visible from the top. An old tower is visible in the west and another in the south-southeast.
Once a suitable site had been found, the construction of the actual tower could begin. Towers were primarily constructed on-site using the wood from surrounding forests. The construction of towers exceeding 40 meters at their highest was laborious and required great skill.
The final double-structured observation tower was constructed between the 17th and the 31st of May in 1922 under Pesonen's supervision. The builders included a master builder, sergeant major, and 10 privates. The tower was erected in 12 days. The trees had been cut down but needed to be deparked. The recognition stand was expanded into an observation tower. The equipment stand stood 70 meters in height, above which light was beamed to the other towers from a height of 27 meters.
The towers always had a double structure. That is, each tower had 2 separate towers, one within the other. The actual measuring instrument was installed in an observation stand in the inner tower, while the observers stood in the outer tower. In some cases, the towers had 2 layers, with the lighting being installed on the upper level of the tower. Due to their immense size, the towers served as excellent landmarks and popular places for viewing the surrounding countryside. For safety reasons, the majority of the decaying towers have since been destroyed in order to stop adventurers from climbing them. The majority of the points were located far from habitation and terrain that was difficult to reach. All imaginable means of transport, including horses, reindeer, boats, cars, and, towards the end, even helicopters, were utilized for transporting the heavy surveying equipment. In the vast uninhabited areas of Lapland, reaching the triangulation points required a lot of effort. Let's listen to the words of one surveyor in Tjurnoaivi during the summer of 1959.
We took a motorboat from Ivala to the end of the Tjurno fjord, from where we rowed a boat to the lake Pitkä Tjurno, going along a stream connecting the 2 lakes. Then we will row the 3-kilometer distance across the lake to the Tjurno homestead. From the Tjurno homestead, we can reach the border by following a direct eastward path. By following the border on foot, the tower can be reached through reasonably dry terrain. The climb to the hill is steep. The length of the route is approximately 22 kilometers and can take 6 men carrying the triangulation equipment about 8.5 hours.
Workers lived close to the site. In inhabited areas, accommodation was easy to arrange at nearby farms. In remote areas, however, tents had to be used. At its best, the measuring took several evenings or nights, but in poor weather conditions, the workers often had to stay at the site for weeks on end. Over the decades, the measurements progressed slowly from southern to central Finland, eventually reaching even the most remote corners of Lapland. In 1970, a new coordinate system, the National Grid Coordinate System, was introduced to Finland. It was based solely on results from the first-order triangulation. In Lapland, the National Grid Coordinate System has at the most a margin of error of less than a couple of meters. In other words, despite the 70 years it took to measure the 1,300-kilometer distance from south to north, the final result only deviates by 2 meters. This proves the accuracy of the triangulation methods used for measuring and calculating distance and position. Indeed, one cannot but admire the accuracy of the measuring methods developed already in the early 20th century. By the late 1980s, space geodatic measuring methods, especially the use of GPS, had displaced triangulation. The same work that took 70 years by means of triangulation could be completed using GPS in a couple of summers. As a result, the use of triangulation in surveying and mapping came to an end, and surveyors with their inver wires and triangulation towers are no longer to be found.